Okay, after you've watched the video for how to get to Archangel, how to use Archangel, make sure you watch that first. Then you can um, set these to path wherever your directories are. And then I use the Sorensen's toolbox that allows me to use the shorthand and asymptotic Bode plots. And then AAV3 will take you to the Archangel program. Now we're going to do loop shaping for the F4 and the landing configuration. So that's our F4. Category C is landing, standard aircraft data file. It's a class 4 aircraft, so I'll pick 1 here. Category C is landing, so I'll pick a 3 here. And now I'm going to escape right away. You can play with this if you like to see all the things you can do. But we're going to go to the pitch rate, or the pitch rate transfer function, which should be Q to DE. So I'm looking over here, and there it is, Q to DE, and we see that it's a transfer function. It's been defined so that it's actually Q to minus DE because it has a plus sign, as we'll see. If I were to look at the Q to DE transfer function, we'll see that he has taken the minus sign out. It doesn't look like it because of the 10 to the minus 15. But let's clean this up with the minreal command. So I'll say QDE TF equals minreal. And minreal will clean it up. So let's see what we get now. Now let's look at the QDE command. And you can see it gave us a nice 0 there. So there's no minus sign in the numerator. This minus sign in the denominator means that the short period is unstable. So the first thing we have to do is to stabilize that. Before we can do loop shaping and anything with gain and phase margin, we're going to rate stabilize because that works 90% of the time. So rate stabilization means we'll feedback rate, which is QDE, through a gyro. That's how we get the pitch rate Q. We're not differentiating anything. We're just using nature's signal of rate through a gyro. So we'll size the tool, QDE, TF, and this should give us a system. We see we have a low gain, we have an instability there on the j omega axis. So we're going to have to raise the gain. And I think we probably should raise the gain until those roots looks like they're going to meet at the real axis, don't they? So my suggestion on this thing, just a stabilization, would be we're going to raise the gain until the roots become equal, just like so, right there. That's pretty close to being equal. And I'll take a look over here in the Bode plot. We've kind of gone off the scale with it. So, but we have rate stabilization. So let's take a look at the step response to see what happens if I give a. So it's kind of crude, but it looks like it's pretty decent. So we're going to go back with this set of gain, and notice the gain is 74. So I'm going to close this, go back to my MATLAB command, and we're going to go to so my first closed loop transfer function will be equal to feedback, and we're going to feedback QDE TF, that's the rate, through a gain of 75, I think it was, or thereabout. So we'll take a look and see what that looks like. My first closed loop transfer function looks pretty good. And notice that I've cleaned up the roots. So now I don't have any roots in the right half plane. So for my next loop closure, which will be on the outer loop, we're going to close theta. So look at the block diagram and make sure you see what we're doing on the block diagram. I'd stop this video here and draw that block diagram to see that you know what we're doing. And our second open loop transfer function, OLTF, was going to be equal to the CLTF divided by S to give us theta, because we have pitch rate closed loop up here. So now we're going to get theta. And let's take a look at OLTF2. So the 0 now is gone in the numerator. And now we're going to feed back theta through a gain. So we'll put OLTF2 and take a look and see. And now let's suppose that our specification for a fighter was that we have a closed loop bandwidth of 10 radians per second. That's pretty normal for a fighter, at least 10 radians a second. So for the landing mode, I'm going to move my bandwidth to get 10 radians per second. And there you can see I got 9.81 down here. Maybe I can squeeze up just a little bit more. That's probably close enough. There's 10.3. So we'll take 10.3. My phase margin is 85 degrees. I don't have any poles or zeros to the right half plane. So loop shaping is going to work on this. So the loop shaping, basically, what I want is something that looks like 20 dB per decade through the 0 dB line and a good phase margin, 45 to 90 degrees or so. And I've got that. So my gain for this is about 780. I'm reading that out in the lower left-hand corner. And this gain is in the forward loop. So look at the block diagram and make sure you see where we're putting this gain. So we have a gain of 780. So I go back to my MATLAB. And now I'm going to see my second loop closure, which is my outer loop, equals feedback. And now I have my OLTF2 times 780, like so. And feeding back through 1. We just have simple feedback of theta. So if I'm looking through my CLTF2, there is a transfer function. You can look at the time constant form of CLTF2. That'll give you the steady state value. And look at my steady state value is just about 1, isn't it? Pretty close to 1. Well, that's pretty good. So it's going to track the input signal pretty well. And let's look at a step command. So there's my step command for the system, and I can look at the characteristics if I want. Settling time looks pretty good, about 0.35 seconds. Bode plot of OLTF 2 times 780, and there's the Bode plot that we've got. And now I'm going to put hold on and look at the closed loop, the Bode plot for the closed loop transfer function, which will give us the bandwidth. And it should both be on the same plot. So the closed loop transfer function is the green line. And notice at 10, if I look at this, maybe if I blew it up a little bit, I would see it would be about 3 dB right at the crossover frequency, isn't it? So the crossover frequency is a little past 10.3, and that's just about where so we can see that the crossover frequency of the open loop system predicts the bandwidth of the closed loop system. And the bandwidth of the closed loop system is the specification. That tells you how responsive the F4 is to stick commands. Okay, that's the end of this video.